Thank you everyone for coming today. A huge thank you to the CNCF, the volunteers, and the staff, and everyone it takes to put on today's talk. I really appreciate some of your time. Today I have a talk put together that was originally titled, You Can Deploy 1,000 Apps to Kubernetes, but Can You Keep Them Up to Date? My name is Liam Randall. I'm founder and CEO of Cosmonic, where we create enterprise WebAssembly. I'm co-creator of CNCF WasmCloud, former VP of Innovation at Capital One, and a longtime open source company builder. I built the very first Kubernetes company in 2014, acquired by Capital One. Before that, I did Corelight, which is built on Brozeek. That's a unicorn. I'm also an investor in a number of open source companies built around OS Query, Cloud Custodian, and many more. I'm incredibly passionate about open source. I love long distance swimming. I've got 3 kids and I live in Washington, DC. If you'd like to talk to me about winemaking, I'm available after the show as well. Let's get started with a few principles about platform engineering. Some things that we want to align on and maybe review a quick agenda. So we're going to start by having an honest look about the state of containers and orchestrators. They've gotten pretty good, but there's still some gaps that are fundamentally inherent in the technology we want to make sure that we align on. Then we're going to talk about what is WebAssembly. We're going to talk about the platform harness pattern, look at a couple of reference apps, and then hack a few things live on stage, which I think is always fun. I'm a big fan of the live demo. You know, we can all live and die by that together today, but I'm going to try it 5 times, so we'll see what happens. Some of the principles that we want to align to today are the principles of least privilege, secure by default, a limited blast radius. The talk is directed at platform engineers, so I'm assuming that many of you think very deeply about things like blast radius, how do I handle thundering herds, and the noisy neighbor problem. Those are the first principles that we're going to continue to go back to in today's talk. But first, a quick question for you, and I'll throw some swag. If you take those phones out, or keep your phones out, and hit that QR code, let me know who you are. For a couple of the questions today, you will have the ability to select multiple answers. For other questions, you'll just be able to select one. So I'll just give you guys a quick sec, just so I understand who's here in the audience, and hopefully I don't surprise somebody too much with those t-shirts. If you get more than one, please go ahead and get them out. That was even the wrong question, but this was the question for later. Where do you run your compute? And it seems like on-prem and AWS are the big winners here. We'll come back to that information later. But let's start with the venerable container. At this point, I'm sure everybody understands that containers are layers of information. But we oftentimes still suffer from security vulnerabilities. And let's get started with our first hacking demo. What I've done is I've created a simple web shell here and embedded it in a variety of containers to make a point. And what we're going to do is we're going to look at code that we've all seen before. It's code like log4j, code that is abused and not used the way that it was intended. It takes advantage of a common weakness that we find in containers, which is a violation of least privilege, bringing too many things into a container here. So some of us have even written code this bad. So what I've done is I've created a couple different containers for this fake company called PersonFacts. PersonFacts is the best PersonFacts. They're instant, they're fresh, and I've embedded it in a variety of containers here, one with Fedora, one with Ubuntu, one with Alpine, and one from scratch to show that we could have more minimal containers. But I want to just make sure that we all align on how bad this can be. And so with this web shell, I can actually just type /command here at the exec handler, and I can then pass commands. So if this were in your cloud and I were a threat actor, I might do something like, let's go maybe download the AWS CLI to this computer, or CLI. I'm not sure who I've offended with that pronunciation or not. And then I might try to do something like, let's make sure that we got it downloaded okay. This is the silliest web shell, but it does indeed work. It's not that much unlike the early versions of China Chopper, if you've seen it. And then you can see I've got the CLI downloaded, and I'm not going to go through the entire exploitation process here of what would happen. What did I do wrong here? But you could unzip this, instruct the command, and then start probing your infrastructure or look for lateral pivots around. And let's try to get this unzipped, because I think that's like the neat thing here. Unzip the CLI. Okay. All right, there we go. All right, so just to demonstrate, we could take this example a little bit further and start pivoting laterally through our infrastructure. If you'd like instructions for doing that in your cloud, and abusing STS and things like that, I'm happy to get with you afterwards. But really what I'm trying to just show is this idea that containers oftentimes let us down in their fundamental properties in one of their designs. My only goal here is to deploy a function to the web, and yet I'm thinking about operating systems. I may only need to use file in and file out for my function, but I'm ending up giving my threat actor access to things like TCP and UDP sockets and things like that. It's one of the things that we find if you start monitoring these things. It's a very common thing that's abused in containers. And this is one of the fundamental flaws that we're gonna lead to when we talk about why we need a better abstraction for platform engineering and tech. Well, what about containerized platforms? You know, there's Kubernetes, but there's honestly some other technologies that are getting really good. Things like AWS Lambda has been great for a long time, or Knative. You know, when we think about these things from a technology point of view, we've all lived through these epics of tech. You know, going back 20 years, we all started with the same idea of, I have a single application mapped to a full computer. This is crazy. I have all this unused capacity, all of this overhead. And the question we ask ourselves at each one of these fundamental epics was, how do I platformize this? How do I share this layer? How do I get multi-tenancy and higher density to save money, to save time, to save cost? And whether we're talking about CPUs with VMs in VMware, with data centers, with AWS and having a shared data center, or with operating systems and orchestration with containers and Kubernetes, we're still asking ourselves that same question. How do we get multi-tenant? How do we save money? How do we platformize? So let's do a quick example of one of the fundamental weaknesses that still remains in this layer. And we're going to take a look at Knative. If you're not familiar with Knative, it is fabulous software. It originally was out of Google, and it's designed to be sort of a lightweight functions as a service. It's usually deployed on top of Kubernetes. So what I've done here is I've just pulled out Knative, and I'm running a couple functions here, including a node function that has scaled to 0. So it's no longer in the pod's memory here. This is a common problem that we want to demonstrate. The first was security. The second here is the cold start problem of what happens when we have to start a container from scratch that hasn't been loaded. Technologies like Knative and AWS Lambda still use containers underneath the hood. And even highly optimized, they're still essentially slower than a network request. So this very first hit, you can see, took 1.2 seconds. And if I run additional hits, they go much, much faster. You can see this one is a fraction of a millisecond. If I hit it again here locally, it's about 1 millisecond. And so these platforms are very good, but they suffer from this problem called the cold start problem. Now, why do you really care about that? Because there's 100 tools out there on the floor that will help you to manage this problem. They will help you to cost optimize, they'll help you to auto-scale, but you still can't get past the fundamental inherent properties that containers take longer than a network request to start. And that means that if you want your container to be available, it needs to be running, whether it's being used or not. And what this leads to is the high cost of cloud computing, what everybody complains about. Because of your SLAs, your SLOs, if you're not familiar with those words, that's the, I need to run multiple copies so that I'm reliable, I'm redundant, I'm available. I now have to run more copies, or perhaps for data locality, for GDPR. You're now spinning up more and more regions. So your cost per application is getting worse with Knative. And Knative and AWS Lambda are not bad technologies. They are great technologies, but they're held back by the abstractions that we've embraced 10 years ago now at this point. So this high cost of today's containers is this second big problem. And it also impacts the density that you can run at. Here on my laptop, if I were to continue to scale, I found that I could lock up my local MacBook. Now, that's not really representative of a production use case where you're optimizing it on Linux, but it is representative of the problem, that if you're running hundreds of containers on a Kubernetes node, you're typically doing pretty good. It means you've got your images, right size down to pretty small. You're not using a bunch of 2 gig Java images or something like that. But this density is now the third problem that we have with containers. They are inherently insecure. They're open by default, the cold start problem, and this density problem that we have here. And this cold start problem is something that people like AWS have been optimizing for years, but even they have trouble getting it past a network request, which is about 30 seconds. Now, you've got a little bit of a preview here of coming attractions. When we get to WebAssembly, one of WebAssembly's unique properties that we have enabled through going back to first principles is this incredibly small cold start time. It's so small, in fact, that it's less than a network request, even if we were in the same data rack. So it's an incredibly powerful technology when we get to it here. But let's talk about the final and the biggest problem with the way that we build today's platforms. And I like to refer to it as the original sin of platform engineering. Now, in the audience, we've got an audience full of platform engineers here, and you are all good people, and you're very kind, and you all want to help your developers to go faster and to check all of those enterprise boxes so that they can just do what they need to do, build functions and deploy them. But the golden template ends up becoming this original sin of platform engineering. What happens is we'll pull together something, typically Java Spring Boot, and we'll include all of our enterprise goo. It'll have messaging, it'll have one Kafka, one Kubernetes, one Lake, one OTel, all of our corporate services that we have in here. But as soon as a developer copies that template, they are on their own. And we end up in the world's worst position, where we have 5,000 teams that each patch one vulnerability, the same vulnerability, one time. And what we really want is a world where one team can patch 5,000 vulnerabilities at once. And the problem's even worse, because our code is not compatible across application frameworks. It's not compatible across languages. And while, yes, containers and Kubernetes are theoretically portable, what happens is that they get anchored into a place and a time, into a control plane. If you're implementing and building on VMware Broadcom today, you are likely stuck there even if you're in containers, because you're using all of these local platforms. Platform engineers don't build a single platform. We integrate and orchestrate platforms of platforms. And this opportunity means that we end up stuck in one place with this original sin of platform engineering. So while people complain about the high cost of today's clouds and cold starts and idle infrastructure and security, what they're really complaining about are these first principle problems with the design of the platforms themselves and the inherent cases. That by default, containers are open. And it does not mean that you cannot lock down your containers or minimize them. They're wonderful projects, or doing things like from scratch containers. Containers suffer from high cold start times, which leads to the high cost of idle infrastructure. They're often bloated, which leads to lower density per system. They're anchored in place. And the killer for me, what I found most painful in my previous role owning platform engineering, is that I'll have 5,000 teams fixing the same vulnerability one time. So how do we solve this problem? Now, may I ask, who's heard of WebAssembly? Okay, I can't see any of you, so I'll just guess some of you. Maybe none, maybe all of you. I can't really see with the lights, to be honest. WebAssembly is kind of a hard technology to wrap your brain around, and I hope in the next 10 minutes that I can help you to really understand it very deeply and why you should think about it as another alternative with containers, with virtual machines, and with clouds for your on-premise infrastructure. So WebAssembly is a bytecode target. It may sound a little bit like Java. It's not all that different, but one of its fundamental reasons that it's different is that it's open. It's a W3C standard on the same level as HTML, CSS, and JavaScript. It has been adopted at a pace like which we've seen nothing else be adopted. It already has billions of users. You're actually probably using it right now when you should be listening to me. If you've got Google Docs open, you're using WebAssembly. If you're on a Zoom call and you've got your background filter, you're using WebAssembly. In the back, watching Amazon Prime Video, you're using WebAssembly. They don't target 8,000 unique devices or build 8,000 binaries for Amazon Prime. They target WebAssembly. Think of it like the tiniest virtual machine. But it's a virtual machine and an ecosystem that is designed with first principles. Now, like a lot of good things, it started in the browser. So it already works in V8, which is Chrome. It already works in Safari. It already works in SpiderMonkey, which is Firefox. And you can even run it on your servers with projects like CNCF WasmCloud, which is incubating. We've got around 350 enterprise contributors there. And there are even a couple of other orchestrators and runtimes that are also in the CNCF. So you've got a couple options here. Now it's neat because there's a standard that's called a WebAssembly component. And a WebAssembly component is like a really tiny virtual machine with a neat property. We declare the inputs and the outputs when we build them. And what this means is that we know how to lock it down. We know that if it only needs file I/O or standard in and standard out, we don't even give it access to streams. We don't even give it access to fork and other things like the POSIX type system calls. Now, it's really easy to compose two WebAssembly modules together, and you're like, Liam, that's dumb. I can compose Rust and Go today. But how do you do it? You build a container, you set up a web server, you set up gRPC, and if it happens in milliseconds, you're like, I'm awesome. WebAssembly is neat because it's language interoperable. So when we have a string in Rust or a string in Go, they're lifted and lowered so that they're the same, and it's smart. So if you've got two things in Rust, it doesn't even shortcut them. It just connects them directly there. And when we compose WebAssembly, we have this share nothing linking. We have separate stack-based virtual machines that are interface-driven, just like Lego blocks. If it fits, I get. And it all happens within a single process. So these WebAssembly cross-process accesses happen in nanoseconds. They're lightning fast, especially when we compare them to traditional sort of microservices that would happen over a network boundary, even on a local host or something like that. So I think you can probably already see where we're going with this. WebAssembly is a little bit like Lego blocks. What if we have a platform Lego block, like a platform harness that the platform engineers can maintain? And what if we give our users a really tiny harness that they can maintain? And that's exactly what we're doing in CNCF WasmCloud, is that sort of approach where we can minimize, embrace the principle of least effort, of least code, of least surface area, and give our developers these tiny functions. Now we have the advantage of every one of these little Lego blocks, as you'll see shortly, is versioned. So standard in has a version, standard out has a version. You can create your own contracts for things like business contracts or GPIO or whatever your business case is, and those all get versioned. So you can start to maintain them independently, and we're one step closer to this world where one team can maintain 5,000 apps at once. We'll do a demo in a moment. So this is our vision for what platform engineering looks like with WebAssembly and CNCF WasmCloud. You have language interoperable platform harnesses that are maintained centrally, empowering developers to choose their business logic approach in the language of their choice. What's neat about WebAssembly is because these are these highly structured interfaces, is that we can design them to be pluggable. So in the WasmCloud community, we've created pluggable interfaces for common platform engineering components, things like key value, things like authentication and secrets. So with secrets, for example, you can choose to use HashiCorp Vault. Maybe you're on your old Broadcom interface. You migrate to AWS and you want to use AWS Secret Manager. Hot swap at the platform layer. The developers don't even know. Maybe you want to use Kubernetes secrets. You can swap that in, and so forth. And you're not stopped from doing tight couplings. People talk about all the amazing power of Valkey and the new performance gains that they're getting out of it. If you've looked at the options for Valkey, there's many. Maybe a generic key value interface doesn't let you access those options. You're not prevented at all from tightly coupling to specific interfaces. And we've had vendors like Cloudflare, who partner with Fortune 50 banks, implement their own interfaces in the WasmCloud ecosystem so that platform engineers can still choose to tightly couple with an interface if you'd like to. So what does this world look like? Now I can suddenly take my components, I can run them across different language runtimes, and because they're pluggable, I can easily run them on any cloud, on any edge, or any Kubernetes, including your own. That's a powerful statement when we're looking at it. So let's look at a demo. Now, all these slides will be open, by the way. I see a bunch of people taking pictures. I'll put them up on the slide share. I want you to have them. I want you to take this message and be able to communicate it to your teams. I'm an open source guy by heart. I do work at a company that helps companies do this, but I'm more concerned about building the community and the effort in the ecosystem in CNCF WasmCloud. So this is a sample application we're going to look at, and we're going to dive through those problems we saw with containers and look at them through the lens of WebAssembly, and we'll see how, by going back to first principles, WebAssembly changes this. Now, this app is a little complicated because we're using it in multiple demos this week, but the parts I want you to look at are this little platform harness piece and this user component. Now, the theory behind this app is that it's some sort of rules engine for interbank transfers, and any bank can post their own rules into the platform. So locally here on my laptop, I can actually run 10,000 of these tiny little components, and I use less than a gig of memory. You'll see in a moment when we take a look at them. So let's dive into the app here. I think the demo's here. All right, great. So this code is up on GitHub already, but I'm going to look at one of the developer harnesses first. And it's a very simple file when you're looking at it. The developer is just writing Go code. And it looks like there's not a lot of Go code here because there's not, because we're actually importing these platform harnesses where we have authentication and tracing and messaging and HTTP and all of those things that may have vulnerabilities that we want to maintain for all of the developers here. And what I find to be really neat about this application is the fundamental size here. So I've pulled up and compiled one of these things, or we can do it on disk either way. Where am I? WasmPay, my camera, build. All right, is that okay in the size-wise in the back of the room there? Now there's a couple different WASM components here that are compiled, and one of these is 7 kilobytes. I said 7 kilobytes. That is the user component. And when we compose it together with the harness, it's still only 265 kilobytes. Really, really tiny. Now, why is this so much smaller than if I'd put this, compiled this as a Go app like I did in the web shell? Even if I put it in a from-scratch container, it's still a few megs. Or if I put it into an Alpine container, it's even bigger. Or from Ubuntu, or whatever image you're using. It's because the only thing I have here are the functions necessary for that particular app. There's no additional interfaces. There's nothing beyond the least that we need to get here. And when we think about why this was designed this way, WebAssembly was originally built and designed for the browsers. The backstory is actually kind of amazing. This great developer over at Google named Alon Zakai had one of those ideas that is so dumb, it's brilliant. He said, what would happen if I cross-compiled C code, transpiled it to JavaScript? And everyone in this room remembers this day. It was in 2012. You were on Reddit. Maybe you're still an old /daughter, not sure about your history. And right at the top of the page was run Doom in your browser. And you're like, man, they're running Doom on everything these days. And you clicked on it, but this felt different because it resized for the window and it was performant. And you were like, whoa, what the heck is this? And then you look behind the scenes because you're curious, you're into tech and you just love to understand how things work. And you're like, ASM.js, transpiling C to JavaScript, this is an abomination. And it was an abomination, but it was the start of a brilliant idea. The browser engine manufacturers at Firefox and at Chrome started to optimize those hot paths, and in 2016, a standard was formed called WebAssembly. And since then, a group of us out of the Bytecode Alliance and many other organizations, this is open, so there are literally tens of thousands of contributors that are helping to build this, have been creating the ecosystem and the community to enable these results. This is supported by your compilers. All of your static tools that compile to LLVM, Rust, C, C++, compile right down. Go and TinyGo have support. We can compile Python on a limited basis. And last week, Oracle even announced that they're working on a Java port for WebAssembly, which is truly the white whale that we'll get to. So these components are incredibly small, and when we spin them up, they give us the ability to build platforms at scales that were previously not fathomable. So here I'm looking at WebAssembly clusters on CNCF WasmCloud that are running across AWS, Akamai, and my on-prem. And we're using the sort of pluggability of WebAssembly underneath the hood here. in order to enable this really high multi-tenancy. So I've got two WasmCloud hosts, which are just executables. You can put them in a container. We ship them with CRDs for all the different layers and an operator, following best practices. So you can use a kube control right out of disk in order to get these things running. They're compatible with Argo, GitOps, all of your other types of solutions. And you can easily deploy them out here. So I've got a number of components here that are running, and I can set limits on them and resources just like I would my other technology here. So here I'm limited some of these interfaces to be 100, and if I actually look at the sort of fake company here, I think I can send $100 in US dollars, but there's a rule that's written so that if I try to send it in Great British pounds, it should fail out because there's a rule there. So transaction failed validation, unsupported currency. So I have a longer demo there with Argo. If you'd like to see it, come to the booth. I am short on time, so I'm going to make sure that I get through the rest of my content here. So maybe next question. I'll throw a couple more swag. What are the most popular languages that you're using at work? Good research question here. This is a nice little purple platform engineering shirt. See, I told you if you sat up front, I was not going to get these very far. Maybe try to get one a little further this time. There we go. Maybe another one right here. All right. And hopefully that's your size. Now you can see a bunch of platform engineers. Go is there, but I would have guessed Java was going to be our big winner here, and I'm not surprised. My conservative estimation is that Java makes up around 60 to 65% of the enterprise microservice market, with what we're seeing on Kubernetes, with Python or Go being a solid number 2 here. So what did we see with that tenant evaluator? We saw really tiny pieces of code that the developers wrote. This is what it compiles down to from an interface perspective. Now, what I'd like you to note from the interfaces here is that you can see that this interface doesn't have all of POSIX, the 500 system calls that are available to it. It has standard in, it has standard out, it has streams, it has some file pre-opens and things like that. But the platform harness itself, when we bring that in, brings in a couple of really critical capabilities, messaging, as well as HTTP. And I'll call out a hidden dividend of this approach is that let's imagine that you wanted to create additional triggers for these functions. You can simply create triggers for SQS or whatever triggers you want and reuse that same harness, because the harness plugs into an interface that I'm calling validation. And on the other side of validation is where I'm sourcing my requests. If that's not clear to you, I can whiteboard some things with you afterwards. So this is a very powerful approach. So if we compare this to why not containers and why WebAssembly, we now have a platform that is capability-based. I start with nothing in my sandbox, and I grant it one capability at a time. I can scale to 0 with 0 cold starts. They're incredibly small, so I can get tremendous density in my platforms. They're portable, not just in theory, but across both clouds, as well as different capabilities because they're pluggable. And instead of this world where 5,000 developers fix the same vulnerability one at a time, I can move to a world where one team can fix 5,000 applications at once. So let's maybe do one more demo, and then I might have time for one question. What about more complicated things? I've got these interfaces. In this particular demo, which I'm not going to execute live, but I can afterwards if somebody wants to see it, I've got an unchecked file input. Could we leverage the power of this component model in order to virtualize that interface? Yes, we can. So here's another view on what we're doing here underneath the hood. We have our platform harness that imports, HTTP and Postgres and all of these databases running on CNCF WasmCloud. A developer is able to import it, but in this case, the developer does need access to the file system. We're uploading files and we're changing them. Well, in this case, we can use a technique called WasmVirt, which would enable us to actually take one of those interfaces and virtualize it into the file system. So developers are completely unaware that they're even running with a virtual file system. Maybe when they're developing locally, we attach them to local disk, and when we run them on our platform, we virtualize it. It's the same sort of component composition. We take our code, we're going to take that file system pre-opens, and we can use that command at the top in order to virtualize it out. And then when I run this at disk, this is open if you want to play with this little exploit later, or you can have ChatGPT create it just like I did yourself. You can virtualize it yourself. So in closing, this is a really powerful approach, and this is not theoretical. At the last KubeCon, we had this amazing talk from American Express, who came out and talked about why they selected CNCF WasmCloud for their platform engineering, what were their requirements, and how they were using the platform harness approach. Just a couple weeks ago, we were surprised by 4 blog posts by the Norwegian Food Safety Agency, which talked about leveraging CNCF WasmCloud for building their platforms. And we have a project from a group of telcos in a thing called the TM Forum that has just crossed 1 million downloads. This is people like Orange, Vodafone, and others that are building their platforms on CNCF WasmCloud. I really look forward to getting to know you. We'll be back at the Cosmonic booth afterwards for questions. We've got the WasmCloud booth out on the pavilion floor as well. If you come to wasmcloud.com, you can click join our Slack. You can come and hang out and ask any questions you want. The whole core team is in there. I think I'm out of time for questions, but I will be available here on the side of stage. Thank you so much for your time.